Okay, now we finally get to start talking about some physics. The first topic we're going to talk about in physics is motion. And we're going to start with motion because it's a topic that we all have a lot of experience with. And we really need to understand some of the basic terms in motion: distance, velocity, speed, acceleration. These are all really important ideas in order to jump off and get into some more complicated and maybe more interesting physics. So this is where we're going to start. We'll start out talking about some straightforward motion. A ball flying through the air, a car driving down the street, things like that. And we're going to get to some more sophisticated representations in the next chapter. But for starters, let's just practice wrapping our brains around this motion with something called a motion diagram. So a motion diagram is, again, just sort of a first step into creating an analytical system where we can understand motion from a mathematical perspective. And it just works like this. Let's say we've got some car moving along, and we can take a series of snapshots. Now, it's important that we have the camera in the same location and at the same angle, and we're not panning the camera or anything like that. But we take a series of snapshots of this car. And lined up like this, we really get a sense that this car is moving from left to right across this screen. But we can capture it all in one image if we overlay all of these images. And if we take our snapshots with equal intervals of time between them, then we can really learn a lot about the motion of the car just from this series of snapshots overlaid like this. We can see that the car is moving, for sure, because it's not in the same position in each frame. What else can we see? Well, it's equal distance between the cars in each frame. Equal distance, equal time. I think this car is probably going at a constant speed as well. So this is a pretty useful representation here, but we can make it even more useful by representing this as the particle model. Now, if we're to look back at this, there's just a whole bunch of detail here that we just don't need if all we're trying to do is understand the sort of bulk motion of this car. Things we don't really care about. What color it is. It looks like it's an Audi coupe. We don't care what kind of car it is. You know what? We don't even care that it has wheels, to be perfectly honest, because a motion diagram for a person jogging at the same speed would look exactly the same. I mean, it'd be a picture of a person instead of a car, but if all we care about is the velocity of the car and how fast it travels, what direction it's going, things like that, then we don't care about a whole bunch of different details. And so we introduce a simplifying model wherein we treat the object as if all of the mass were concentrated at one point in space. And this helps us to focus on the important aspects of the motion. And we do this all the time, right? This simplifying of things in order to wrap our brains around them. A lot of times when I introduce this to students think that, oh gosh, why are we starting out with such a simplistic version here? Why are we not trying to wrap our brains around the complete motion of the car? Well, this is just what we do, right? And we do it without even thinking about it. We apply simplifying models, you and I, all the time. Even if you're not a physicist, you apply simplifying models all the time. For example, earlier I had this ball, and I threw it up and down here, and I said, hey, we're going to focus on the motion of this ball. And none of you were like, oh, that's not a ball. That's a collection of atoms that have formed themselves into molecules, and it's some kind of a plasticky kind of a molecule. And, we got to remember that there's electrons. No, none of you were like that. We all, in our minds, without even thinking about it, we combined this collection of an uncountably large number of objects, all of the atoms and protons and neutrons and electrons that make up this ball. Unconsciously, we all grouped it together and said, ball. And we didn't even worry about it, right? And I'm the only one talking about it, right? So we do this all the time. And furthermore, there is just absolutely no way, even for a very simple motion like this, there is absolutely no way that we could ever wrap our brains around everything that's going on here, right? There's probably something like, 10 to the 23rd or 4th atoms in this ball, right? So that's 23 zeros if we're going to count all the atoms. Each one of those has a bunch of electrons, a bunch of protons. if we wanted to keep track of everything that's going into this ball, everything that's happening when I do some simple motion like this, you just can't. There's just no way. Not even the most powerful supercomputer could do it. I don't know that I can't even imagine a supercomputer being powerful enough to do that, right? I mean, it's just impossible, right? And so we have to apply simplifying assumptions. We have to. And so that's why we're going to introduce this idea of the particle model. Whether it's a ball or an Audi or a Buick or a piano, we're going to represent it with a dot. All of the mass is concentrated at the dot. Now when we start talking about rotating objects and things like that, then we'll have to expand beyond the particle model, but only when we have to. And so now this is the motion diagram of a car stopping. And we can see, how can we tell it's stopping? Well, again, the pictures are taken with equal time intervals between them. And we see that the car is traveling less distance in an equal amount of time. Less distance in an equal amount of time is less speed. This must be a car coming to a stop. The motion diagram using particles looks just like this. Now, most of us don't count from 0, but in this case, this is sort of like time. Imagine this is the shot at 0 seconds, this is at 1 second, this is at 2 seconds, and this is at 3 seconds. So this is the particle model. Okay, the speed of an object. Speed is a notion that I'm sure you have all had practice thinking about. I suspect I'm not going to blow anybody's mind by telling you that speed is distance traveled over a time interval. So here we see a particle model motion diagram for a car and a bike. And the only way we know the difference between the car and the bike is, of course, because they're labeled, right? So we could analyze these, and we see here, these are all taken at 1 second intervals. So this is a motion diagram. It's been created by superimposing images of this car traveling on top of each other and then replacing the images of the car with a dot. And we see that in both the bicycle's case and the car's case, the dots are separated by 1 second. However, notice that the car travels much farther in 1 second than the bicycle does. Therefore, we can say that the speed of the car must be greater than the bicycle. Now notice this is distance traveled over a time interval. Recall that distance traveled is a scalar. Since distance traveled is a scalar and the time interval is a scalar, then speed is a scalar. And in fact, your speedometer in your car is aptly named. It tells you the speed. It doesn't tell you what direction, it tells you the speed, and speed is a scalar. Let's do a real quick example using the numbers on this picture here. So it says, what is the speed of the car and what is the speed of the bicycle? Well, we know that speed is distance traveled in a time interval. So, for the car, the speed is distance traveled over the time interval. Well, how far did the car go? Well, this is going to be delta x over delta t. X final minus x initial. It looks like the car ended up at 80 feet. And it started at 40 feet. And it took 1 second to get there. And so the speed of the car is 40 feet per second. Predictably, we'd expect the bike to be slower. Let's just see. In this case, speed equals final 40 feet minus initial 20 feet all over 1 second. So, what is the speed of the bicycle? 20 feet per second. And we don't need to include a direction because speed is a scalar. How does that compare to velocity? Velocity and speed are words that get used interchangeably in everyday life. In physics, they mean different things. Velocity is a vector. So speed is a scalar and velocity is a vector. We could say that speed is the magnitude of the velocity vector. The velocity, the average velocity, is the total displacement over the total time interval. Notice that since displacement is a vector, the average velocity is also a vector. And so, let's apply that to this situation here. In this case, my velocity of bike 1 is going to be final minus initial position, so that is 20 feet, minus 0 feet over 1 second, 20 feet per second. How about for bike 2? Well, velocity of bike 2. Well, bike 2 ended up at 100 feet, so final is 100 feet. Minus initial is 120 feet. All over 1 second. And so notice that this is negative 20 feet per second. Okay, so now we have found the velocity of bike 2 and the velocity of bike 1. Notice that the only thing different here is the direction. And where does the direction show up here? Right here. Right? So bike 2 is moving in the negative direction. Bike 1 is moving in the positive direction. And like I said in a previous lecture, if we're in one dimension, then plus and minus is sufficient to indicate the direction. So we don't need an angle here or anything like that to indicate the direction. So, do these two bikes have the same speed? Yeah. Do they have the same velocity? No, they don't. It's kind of tricky. Again, velocity includes direction and speed doesn't. So if you've got your car and you've got a speedometer and a compass in your car, some cars have that, then together that makes a velocitometer. Your speedometer, again, does not include direction because speed is not a vector.